Okay. Looks like a good idea. We start a little bit late. I can see a lot more people here now. That's fantastic. Good evening. Nice of you to join us, join me. My name is Mads Wilson, and I am from a group called Copenhagen Suborbitals that are located here in Copenhagen. How many of you know us beforehand? Okay, a few. That's good. And for the rest of you, I will explain what it is that we are doing. So we are all volunteer group, and we are based out on the old B&W shipyard, not far from here, where we have this workshop. And long story short, we are building rockets. Our dream since 2010, I think it is, has been to build a rocket that is just good enough to put a human in space. And when I say in space, I don't mean to the International Space Station or orbiting the Earth or anything crazy like that. I'm talking about a mission just like the Americans and Russians did back in the 50s, a suborbital mission, just up over the Kármán line, which is the official where the official limit to space is, 100 kilometers, and then back down again. That is a trip that takes approximately 15 to 20 minutes. And this is not all, it's not all fantasy. We have flown several different kinds of rockets since 2011, the biggest one being the Heat 1X. Some of you from Denmark might remember that weird looking rocket with a little dome on top that when we launched it turned out to be a bit banana shaped, and hence it didn't really fly straight, but that's another story. And we do this, we launched these rockets from an area called ESD-139, which is a military shooting area just outside of Nexø, Bornholm. This is a sweet spot. A lot of people, both yesterday and today, have asked, but how do you get permission to do this? And the short answer is we don't need permission, because there's no laws, there's no regulations that prevent us from launching rockets, and especially not because ESD-139, this area out here, is just outside it's called the 13 nautical mile limit, which means we are technically in international waters. We are not in Danish territorial waters anymore. We are in international waters, but we are still within the European Union's export zone, which means that we are in international waters, but we are not exporting rocket technology outside the EU, and this is very important. And also, ESD-139, as I said, it's a military shooting area, and that means a lot of things get a lot easier, because we can call Swedish air traffic control and tell them tomorrow at this hour there will be a launch to unlimited height in the area ESD-139, and then they say, okay, we will redirect plane traffic so that there's no planes coming over here. And we can also notify the military, we can notify all the governments surrounding the Baltic Sea, and everybody knows what this means because of that area, because this is an area that has been used for military exercises going all the way back to the Cold War. This comes with a drawback. It's a sweet spot in the way that we can do it, but it comes with a huge drawback because we need to do everything from sea. And for those of you who know about rockets and have watched rocket launches and seen all the people involved, this is not a small operation. There's pardon me, there's a shit ton of systems, computers, people, procedures, all kinds of stuff that needs to go hand in hand and all be synchronized. And doing that at sea between land and various vessels that's quite an undertaking. For example, if you're doing something on the launch platform and you all of a sudden realize that you have forgot the 10mm wrench, then you don't just go back to the workshop and get it. You need to use the radio to call for a speedboat that needs to go over to the control ship, and then you just hope that someone on the control ship brought that toolbox that day. And that can, we have had instances where that has slowed down our launch significantly. We haven't missed the launch window, but it was very close at some point. But what I'm mostly going to talk to you today about is failures and error handling. This is a software technical conference, right? So I will try to focus on all the things that we have experienced going wrong. Some of it have involved computers, some of it was pure human error, but it is still interesting because it says a lot about how you manage things when technology and the real world are interacting. We work from a concept in Copenhagen Suborbitals that is everything needs to be just good enough. We don't want to overdo it. For example, when we look at how SpaceX and NASA, how they are building their rockets, everything is about squeezing out those last 10% of efficiency, because efficiency means that you can put some more weight on top of the rocket. That means you can bring more payload, and so you can make more money, right? We are not here to make money. We are just here out of pure interest to show that this can be done. And just a small comparison. This here is the SpaceX Starship. This is a to-scale drawing. And this is the Falcon 9. This is the Blue Origin. And here is our upcoming Speaker rocket. That kind of put things in perspective. Normally in rocketry, for some reason in recent years, people are using bananas for scale. You know why? When you post a picture on social media, for example, of rockets or rocket engines, there are governments and agencies all over the world getting very anxious. If you have anything in these pictures where you can deduct the scale and see what are the exact measurements of this thing, then especially the agencies are getting nervous. So someone somewhere came up with the idea to use a banana, because everyone can relate to a banana. It says something about how the scale is, but obviously using a banana in this size here would be not very intuitive, would it? No. So I have brought this little video to show you how the flight will look, and we tried to get the sound working, so I apologize for that, but let's see. All right, we are software armed. Rocket is in internal power. Guidance navigation computer is armed. Everybody, the rocket will launch from sea. The astronaut will be here. Hopefully the hatch will be closed when we get to the countdown sequence. Data is go. We are go for launch. Order sequence start. T-minus 30 seconds and counting. To do this, we need a quiet day. We need waves not bigger than 1 centimeter, because otherwise the rocket will warp too much to the platform. 1,000 meters. We have main engine cut off. Nose cone off. simplicity, that is it. But as you can see in this video,
And we have
there are a lot of specific things that need to happen in the complete and exact order for this to work, right? Going up will take approximately 50 seconds until the main engine cuts out. At that point, the astronaut will be, or the rocket will be accelerated to somewhere between 3 and 4 times the speed of sound. And when the engine cuts off, there will be so much inertia in the rocket that even if it cuts off at around 50 kilometers, the rocket will still coast up to over 100 kilometers, and then the capsule will separate. And going up is the not so dangerous part of the mission. The second the capsule separates from the launch vehicle and starts coming down, this is the difficult and dangerous part. Because going up, we have computers and gyros that can control the rocket, and we can guide it. But once the engine cuts out, we have no way of controlling anything. We can correct the capsule when it's separated, and try to make sure that we have the correct end pointing down. But the only way we can really do it is by releasing what you saw on the video, a small, it's not a parachute, and it's not really a drag. It's a drag device. It's called a balut, made of a Kapton or Kevlar, so it's heat resistant. And its only purpose is to create a bit of drag so that the capsule turns the correct way down, so that we have the heat shield in the bottom and the parachute end pointing upwards. Because believe it or not, one of the most difficult parts of this entire thing, if we're talking about control and computers, is to determine which way is up and which way is down. Have you ever thought about when you know, in all of our cell phones there's a gyro, right? That we all use for games and all that kind of crap. Have you ever thought about that gyro is somehow always right? No matter what you do, it may not be that precise, but it's always right. And that is because they're cheating, the people who wrote the software that is in the gyro. Because they always assume that they have a 1G vector pointing somewhere. So everywhere the software just looks for the 1G vector in the gyro. Because the software and the hardware is made specifically for devices that are meant to be used near the ground. They are not meant for something that flies. So there will always be a 1G vector, and then they just look for that and say, okay, that is down. But if you take that device, that gyro, and put it on a rocket that accelerates with 3 or 4 Gs that way, then all of a sudden you don't have the fixed 1G vector pointing downwards anymore. So you don't, your whole coordinate system has changed. You don't know which way is up and which way is down. And have any of you worked with gyros ever? For games or anything? A little bit. The problem with the gyros is that when you interpret the data from the gyro, there's always a little bit of noise. Of course, the more expensive and the better the gyro, the smaller amount of noise. But there's a little bit of noise always. And then when the CPU integrates that to calculate the resulting force or where you are in the coordinate system, then that error accumulates quite fast. So after about a minute and a half, then the gyro has no idea. Well, it has an idea, but it's not right. So you don't know which way is up and which way is down, and that is the difficult part here. So when we have the capsule floating in space, the only way we can know for sure is to create drag so that we make sure that we have the correct orientation, because all that energy that we put in the rocket going up, it needs to go somewhere when we descend with the capsule. And the only way, the only place it can go is it can be turned into heat in the heat shield, and that will be hot. Really, that was what what was it? What was the space shuttle? Was it the Discovery that disintegrated on the way down? That was because of this. They had a malfunction in the heat shield. A few of those little square pieces underneath the space shuttle had fallen off, and that resulted in total loss of the spacecraft. So this is quite important. Do any of you now think, why is that rocket so small? How have they chosen the dimensions of that rocket? No? Okay. I remember I said we need to design something that are just good enough. When we do design like this, we start by looking at what is the main objective of our flight. The main objective is to send the astronaut up and bring him down in a way that will not kill him. So the first thing you look at here is how much punishment can a human body endure without being permanently harmed. And luckily, we do not need to test that, because someone did that for us. Back in the 50s, the American Army did a lot of experiments with people using rocket sleds to see how many G-forces the human body could withstand in different directions.
On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. He suffered no serious or permanent ill effects from the 55G peak deceleration load he took. Beading subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track.
Basically, what they found out back then was that the human body has limits in different directions. So let's say that we did what we initially tried to do, create a rocket where the astronaut would be standing up or almost standing up like this. That is the worst possible position that you can orient the body in terms of G-forces. You will have no blood, all the blood will be rushed down in your feet, so you will faint very quickly, and then in a matter of tens of seconds you would probably die. The other way would be even worse, but that is not so feasible, luckily, that have an astronaut standing on his head in the rocket, so we can omit that. But the best way of doing this is to have the G-forces coming forward. That means lying on your back like this. And that is because you have the forces perpendicular to your spine, so you have no crushing of the spine, and also you are oriented in such a way that the G-forces will pull the blood into your torso. That is why in the Apollo capsule, for example, the astronauts are on their back with their arms like this and their knees bent upwards, because then all the blood will be in the head and the torso, and the body can take a lot of G-forces that way. The next best way is the way that the Russians did it back when they designed the Soyuz capsules. That's something called the Cashback position, and it is, you're still curled up like this, and just tilted slightly backwards. If you have seen pictures from the Soyuz capsule, it is a lot more cramped than the Apollo capsule. And the astronaut sits like this. So you still have the G-forces not directly up the spine, and you sit in a way so that you can still curl down and have the blood in the within the torso and close to the heart. So our design criteria became, how small can we design a capsule where the astronaut can sit in that position? And we did a lot of testing. We have built some mock-ups and tried to fit the biggest one of us in there and see how he could fit. And it turned out that about 1 meter in diameter-ish. Then there's still room for the heat shield, and we still have room enough to build a double wall capsule, so that if the outer hull, if something happens to the outer hull, then there's still some protection. It will be a tight fit. It will not be extremely comfortable, but at least in theory, he would be able to survive. And remember, I said just good enough. Another design criteria we always have is, if we can find something that is standard, then we try to use that instead of using something that is non-standard or a little bit out. And it turns out that the standard size that you buy steel and aluminum plates, when you roll that to a tube, it becomes 9.75 or something. So almost a meter in diameter. So we don't need to buy materials in weird sizes or weld anything up. We can just take a standard plate and roll it, and then we have a tube that is big enough for the capsule. Okay. Error handling. Did any of you see the Heat 1X launch back in 2011? The first rocket we built? On that one, we killed the astronaut 3 times. We killed him going up because we crushed his spine. Then we killed him on impact when he hit the water because the parachutes didn't come out. And then we drowned him. And that was using a rocket with a hybrid, something called a hybrid engine. And after that, we thought, okay, we need to build technology a little bit different. We need to use something we can control. Hybrid engines, and I won't go into details about that. You can go into our YouTube channel or whatever afterwards and look at it. Hybrid engines are very simple to build. It's basically just a tube with something in it, and then you pour oxidizer down and you burn whatever. I have seen people building hybrids with frozen sausage or cardboard or whatever. You need something that can burn, and then you put some oxidizer in and it burns. They are very difficult to control. There is a reason why everyone is using liquids. So we thought, okay, let's try to build a big liquid-fueled rocket engine. Confident as we were like, what can possibly go wrong? Let's do that. We'll just build it to size the first time. 2, 6, 5, 4. That we didn't need to test the engine itself first, but could just build the rocket around it and just do an all-up test and test everything, because of course it would work the first time. What you see here is a slow motion footage of that engine test. This is recorded by a GoPro camera that was mounted about a meter from the rocket engine. And what you see here is a catastrophic failure, a small rupture in the welds of the engine that resulted in all the fuel, all 600 liters of alcohol poured out in about 5 seconds. And at the same time, it was fueled by poor oxygen, just oxygen, plain, clean oxygen coming down slowly, feeding the fire. Everything burned. The only reason why we have this footage to show is because the cable ties that held the GoPro melted before the camera did. So it tumbled down and landed down in the water pit, and our guys had to take it apart afterwards, and literally they desoldered the chip with the information on and put it in some other electronics to get this video out of it. And we got some free GoPros from GoPro after that. I'm not sure that they had any idea that their cameras could tolerate this kind of punishment. So it was a fantastic day. I remember the smell of alcohol to this day. We were standing about, I think we were like 50 meters from the rocket or something, and it just smelled like vodka everywhere. And we had been working on this rocket for about 2 years. And you would think that people were disencouraged, right? But I clearly remember looking around and people, and for the first couple of minutes they were like, oh, and then in a little while, you could see on people's faces they were like, let's go build another one. But obviously, we had to do it differently. And after long debates, Copenhagen Suborbitals, we have a completely flat organization. So we don't really have anyone telling anyone what to do because we are all volunteers. It has advantages, but it certainly also has drawbacks sometimes. It's like can be like in a kindergarten, right? But after long debates, we decided that we needed to master all the flight events because it is not really in terms of controlling things, and this is where the computers and software comes into the picture. In terms of controlling things, it doesn't really matter how big the rocket is. It is the same events that we need to control, and it doesn't matter if we go to 100 kilometers or 10 kilometers, as long as we can do all the things in the correct sequence. So we decided to build 2 smaller rockets, Nexø 1 and Nexø 2. You can see the one is slightly smaller than the other, and this is because the Nexø 1 is a little bit simpler. The Nexø 1 has no dynamic pressure regulation, and that means that the fuel is pushed into the engine just by pressurizing the tanks. And for those of you who have a little bit of math or physics knowledge, that means when you have a pressurized tank and you open a valve, it is the same as just releasing a balloon, really. There's no time when the tank is emptying itself. There's no time where you have the same pressure. It's like a weird pressure curve. And that means that the engine is not really functioning at an optimal level at one point, but only at one point. And that makes it difficult to control, but it is simple to build. And then Nexø 2 had the dynamic pressure regulation. You can see here is the Nexø 1 and 2 IKEA assembly kit that we ordered. And you can see down here, this is the engine parts, because we also designed, and again, we spent a couple of years doing just this, and you can go into the YouTube channel and look, there's a ton of tests. We designed and built this little rocket engine because we wanted an engine that was not performing very efficiently, but it was supposed to be rocket and stable, and we needed to know exactly how it would handle itself at work. So we built that and we tested it, I think, 50 or 60 times until we were certain that we could control it and that everything worked. We had previously done some tests with active guidance, so both the Nexø 1 and the Nexø 2 were also equipped with a gyro-controlled active guidance system. This is where the up and down problem also comes into play, because the guidance system is in itself not a really complex system. Do any of you work with controlling hardware? No? Feedback mechanisms and all that? One of our computer guys said that controlling the basic algorithm for controlling a rocket is not much more, it's not much different from controlling like a oil heater. It's all about, in a heater, it's all about hitting a certain temperature and then making sure that the boiler stays within that temperature. It's a feedback loop. It's the same for a rocket, really. The only problem you have with the rocket is that you have a lot of parameters that changes. So when the rocket is flying, the tanks are getting empty, which means that the center of mass and center of gravity is changing. So and you don't have the same weight, and you don't have the same inertia, which means that for one calculation, when you start the flight, then the movement of the rudder will result in one movement, but if you go up 2 kilometers more and the rocket is half empty, then the same movement will not yield in the same reaction from the rocket. So that is quite difficult to implement, and you need to make a lot of assumptions. And this is the important part here. the easiest way to do it is to implement a table where you say at any point during the flight, we expect, because we know how the engine is performing, we expect that the mass will be this and this, and we expect that the center of gravity will be this and this, simply just by calculation, because you know how much fuel the engine will consume. So we did that with the Nexus 1 rocket. We launched that, having all the software and hardware tested and in place, and then this happened.
We are losing power. This is Fido here. I have no altitude on the rocket.
Kommer ned, ja, vi kommer ind til os. Der er ingen go. Der er intet.
We have a rocket in free fall. The parachute is very down. And we have splashdown. Blå rib, ser du det?
Yep.
Jørgen, who sits right there, is my witness. It sounded like that day, also when you were there. The guidance system on the rocket is the gyro controls, but it's also a state machine. That at every given point during the flight, there is a new step, and then it just moves through steps all the time. What happened here was that the rocket, and this sounds really strange, it ran out of fuel. Remember I said that we have this table where it's calculated all the way how much fuel is left. The only reason, or the only time where that works, is when the engine performs as expected. If the engine doesn't perform as expected, then that table will be off, and then the computer doesn't know how to or when to move to the next step. So what happened here was that it was a very, very, very hot day, and we had problems loading the liquid oxygen. Remember, liquid oxygen is minus 183 degrees, and it was about 30 degrees outside and very moist, so we had a lot of boil off, and the oxygen was boiling in the tank. At this point, we hadn't yet developed technology to measure how much oxygen was in the tank. It's easy to measure fuel or alcohol because you just pour it in a can, measure 25 liters, put it on the tank, that's it, right? Liquid oxygen, not so much, because it's boiling and you need to transfer it with pressure and all that. So the way we did it was, and this is almost, thinking about it now, it is almost impossible to imagine, we put the rocket on a weight. So on the launch platform, the rocket was on a weighing cell. And then when we were loading the oxygen, we tried to calculate how much oxygen were in the tank by weighing the rocket. That is quite difficult when you have something at sea that is moving like this, and at the same time the liquid oxygen is boiling off the tank, right? So we didn't have the correct pressure. And at the same time, we had this whole machine set in motion. We had all the people there. We had a launch window. So we made a decision. We said, or Thomas, who was the flight director that day, said, okay, this is good enough, let's try. So he pushed the button and we flew. But because the pressure was off in the oxygen tank, and remember on the Nexus 1 we didn't have the pressure regulation, that means that the fuel and the oxidizer ratio in the engine were a little bit off. And when that ratio is a little bit off, then the chamber pressure from igniting the fuels in the engine is wrong, and it doesn't fit the calculations. The counter pressure from the engine to the tanks is then also wrong. What happens then is it uses more fuel, then the ratio gets more off, the pressure is even worse, and then it just consumed all the fuel too quickly. So at about, I think it was like 30 or 40 seconds or something, not even 20 maybe, the engine just cut off because there was no more fuel. And then the computer looked in its table and said, that can't be right. We are not at cutoff yet. I must have lost the chamber pressure sensor. I'll continue. And then Thomas, we were looking at it, we could see the rocket, we could see it was falling down. Thomas pushed the parachute out button, and then we encountered problem number 2, because it was not implemented in the state machine that if you go to an event that is after an event that is supposed to happen, then it needs to go back and trigger the previous event first if it hasn't been triggered yet. So he pushed the parachute out, and we can see on the gyro, on the accelerometers, all the data we got from the rocket. We can see that the gas generator, the way we do that is we use airbag cartridges to push out parachutes. The airbag cartridge exploded. That was like inside the rocket, but the computer should have gone back and said, "Oh yeah, that's fine, mister. You want to push out the parachute, but you haven't taken off the nose cone yet." So the nose cone was on when it tried to push out the parachute, and obviously the nose cone just stayed on, and the parachute was in there, and the rocket just turned around and hit the water. Okay. We got a lot of valuable data from this, and this is where the error handling comes into play. Sometimes a failure is better than a success, because if we haven't tried this and haven't learned all this, we probably wouldn't know, and we might have flown several missions after that with errors that we didn't know were there. It's the same when you see SpaceX now flying their Starship that explodes midair, and all people go like, "Oh, that's a huge failure." No, it's not a failure. They are just testing it. They are using like some people do, the iterative process when you do software development. Instead of trying to specify everything, let's throw something together and see if it works, and then we learn from the mistakes, and then we implement something else afterwards.
T-minus 10 seconds.
This is the IMU data that came down from the rocket. And here you can see exactly how it performed. And this data that we logged. This is about now Thomas realized that it was going down.
This is Fido here. I have no altitude on the rocket.
Kommer ned. Ja, vi kommer ind i så også. Der er ingen go. Der er
Had the nose cone been off at this point, it wouldn't have been pointing downwards. It would have gone into a flat spin and landed much more soft, but it didn't. You can see it was quite. I'm actually surprised that we managed to get this out of the water, because it was quite beaten up. Some of our physicists they did some calculations, and they estimated that, you see these here bulges here. This is not from impact. This is from water pressure. So they estimate that it has been down somewhere between 30 and 50 meters underwater before it came up again. Yeah. 80 and 90 meters. Yeah. Incidentally, this area here is almost just on top of the Nord Stream 2 pipelines. Remember when they had that drone down, when they said they found something? We have lost several rockets in that area. So some of us were thinking like, holy fuck, whatever. I hope that we remember, or I hope that the stickers peeled off before it went down there. The Nexus 2, again, you can go to our YouTube channel and see. This is Nexus 2 was a fantastic day, and it was a fantastic flight, and it came down in the parachute. But in terms of what we're talking about today, it's quite boring because everything went as planned, everything worked, all the events were in the correct order. The only little issue we had was that we had a receiver, the telemetry receiver lost power, so we're missing like 30 seconds of data, but that was when the rocket was already in the parachute, so it doesn't really matter, we have everything. So the next step is now to build the big rocket. But we are not getting as far as we wanted. And one of the reasons why is because Copenhagen Suborbitals and this whole business about building and launching rockets is 20% rockets and 80% other stuff. We have spent, during the pandemic, we have spent years doing lobby work and fighting with the government because they wanted to pass a law that would ban any Dane really from launching a rocket anywhere or participating in a rocket launch. We have our organization, as I said before, we have had to build tools, to build tools, to build tools, to build a component for a rocket. We have the booster group doing CFD calculations and designing things, everything we do. So every time we build something based on what we have previously learned, we are very careful not to overdo it, but to make sure that when we have some hardware or we have a tank, we have something, it needs to be good enough. It needs to be able to do what it's supposed to do. Not more than that, but it needs to do what it's supposed to do. We have had a lot of tests during the year. This is Job, if any of you have a business and at some point would be hiring and he applies, hire him immediately. He is one of the most talented people I have ever met. He's, I think he's 28 or 29 now, and this was his bachelor project. He built a complete hydraulic gimbal system for a rocket engine, and we tested it, and it worked. You can see this is the test of the BPM-5 rocket engine. This is one of the examples that took a lot of time. Have we had more money, we could just take all the boring bits and say to a company that specializes. For example, tanks, fuel tanks and oxidizer tanks. There are loads of companies that are specialized in doing that. They're very good at doing that. You pay them some money, then they deliver you a tank to specifications, but we don't have that kind of money, so we need to do it ourselves. And to do that, for example, we needed to design a tool that could do weldings on these rounded plates so that we can build a tank, and that takes time. We have the whole capsule development. This is a 3D mock-up of how the capsule will look. There has been a lot of testing going on we don't have access to a wind tunnel, but up north of Copenhagen, there's this place called Copenhagen Air Experience, where you can go and put on a kind of a pilot suit, and then you can float in the airstream. And that place is perfect for testing capsules and small parachute models. So they lend us their little fan once in a while, and we do a little advertising for them, and that's fantastic. But the team has been spending a lot of time on that. And parachutes. In Europe, there is a rule, for some reason I cannot fathom, that you cannot test an experimental parachute by dropping an object with that parachute on. It can only be tested by a human. So we design and build all our parachutes ourselves, but the only way we can test them, this guy here, he's called Ahmed. He's a very, very good skydiver. I think, Jørgen, what was it? He had 5 parachutes on during this jump because he needed to test 3 of our parachutes, and then he had his own suit and then his spare suit, right? So the only way we can do this is having him jumping out of a plane and then releasing our parachute, and then at about 1,500 meters or something, getting rid of that, and then coming down in his own parachute, and then we spend the rest of the day searching for that parachute that has landed in a field of corn somewhere. But that is the only way we can do it. It would be a lot easier if we could put a tracker in it and just drop a sack of potatoes or a concrete block or something and throw it out of a plane, but you can't do that. And this is where he's testing the parachutes for the capsule. We are working on the capsule itself. We're working on the seating for the capsule, and that involves a lot of testing on how the fit of the seat will be, but it also involves some testing in, and we haven't really reached that part yet. How the capsule and the electronics will function in vacuum. We had a fun story. Remember the lander Philae that landed on the comet some years ago? That little thingy that set down a lander, and then it fired some harpoons, and there was some issue because the harpoons didn't really attach to the surface. About a year before that, we had done some testing with the nitrocelluloses, and we have tested that for explosive bolts and for parachute ejection, and we found out that the nitrocelluloses didn't work very well in vacuum. Basically, when you have it at ambient pressure, it goes like gunpowder. When you put it in vacuum, it just says and nothing really happens. And we posted a video on that on YouTube and forgot all about it. And then a few weeks, I think it was before the Philae landed, we got a call from the Max Planck Institute in Germany. We are interested in your results with nitrocelluloses, because we have this lander that are supposed to land on a comet soon, and we used nitrocellulose for the harpoons. So apparently someone didn't think about that. So it's not just us making stupid mistakes. I think they got a lot of good data, but that was quite fun. That's something we just did for the fun of it, really, or to try to do something simple. Was that someone else also made that mistake. Copenhagen Supporters is a crowdfunded project. So it is people like you who pay the bill. We have about 500 supporters from all over the world that pays us $5 to $10 each month as supporters. So we have a quite large PR department that takes photos and videos of everything we do, because it's very important for us to post as much as we can and put it out there, so that the people supporting us can get something back and feel that they are a part of the project. We have had some problems with that during the pandemic. It was difficult for us to meet, but luckily that has been picked up afterwards. So we try to post as much as we can within the limits of the various agencies and their nervous tics. The rule is that you can post anything that you can deduct from a textbook, or anything that you can learn from a textbook. That is okay. But when you publish something that is directly, that you can copy directly, or that is more than textbook material, then you are breaking the international spreading of arms treaty and terrorist act and various. It is not as bad as in Europe as it is in the US. We have had incidents where some of our members were held back by the border control in America because they found some rocket stuff, saw some, I don't know, I think that they're monitoring social media and stuff. They were withheld and had their stuff searched, and it took some time before they were allowed to leave. But it is serious business. I mean, it's nothing to joke about, because especially in the States, the Anti-Terrorist Act can give you a one-way ticket to Guantanamo if you're not careful, and you don't want that. So we try to be very careful. When we started this, we wanted it to be an open source project, but that is just not possible. Open sourcing a missile. We do live stream every time we do a launch, or every time we do a major test, we do a live stream, and that also was a challenge. Again, this is a part of the 80% that is not rockets, because when you don't have the money to buy satellite time, how do you live stream from a ship 30 kilometers out in the Baltic Sea? And I can tell you, the way you do that is with this. This is a old radar dome that has been rebuilt with a ubiquity access point that has been hacked a little bit. And that that little access point is sitting on a platform that is GPS controlled, so that it's always pointing towards land. And on land, and this is quite ironic, we have borrowed the old defense intelligence listening posts in Bornholm. We have got permission to put up our antenna there, so it is pointing to that, and they have a fantastic fiber connection, and then we can use that to broadcast. We had some issues with that during the first launch. Again, sometimes even the less important things has a tendency not to be tested so well. So in the software that were implemented in the first version of this, it was implemented in such a way that it thought that the island was spinning. So that took some effort. I was sitting there for that launch, and we had someone else on the ship, and we had to sit and correct. This sounds so stupid. We had to correct for the rotation of the island to make sure that we had the radio contact between the two towers. And this is where all the broadcast happens. This is Peter. Peter, he has written a distributed video mixer that can control cameras over a unstable network 30 kilometers from land, and then all the streams are sent back to him in Copenhagen, and then he's mixing it and sending it to YouTube, and all that with a 20-second delay. That's pretty good. And he wrote everything from scratch. And this is the only part of our project that is open source. It's called Snowmix, and it's on GitHub, and everyone can download it and play with it. It's quite nice. Then we have our electronics department. We are writing our own software. This is actually me sitting here. This is our FIDO software, the program that controls where the rocket is, how the flight is going, and more importantly, I have a map here of the area that are connected to the AIS system, the positioning system of ships, so that I can see on the screen where all our vessels are, but I can also see where all the other vessels are. The next version of this will also be connected to a digital radar, so that we can compare, so that we can see both the radio GPS signals, and we can see the radar images also, because those two can differ sometimes. We have to design and build everything. Remember I talked about the weight on the platform? This is the first attempt, the Porcupine. This is the first attempt of designing a cheap way of determining how many liters of liquid oxygen in the tank. This is just thermocouples put at different levels in the tank, and then we measure when each of them get hit by the level of oxygen. This has later been replaced by we were doing a project with a company, and they borrowed us a American cryogenics capacitive sensor, and this is the way you do it. This is the way you do it professionally, how you design something to measure a liquid, a cryogenic liquid. It is, for those of you interested in that kind, it's two tubes inside each other and then an oscillator, and then you measure the difference in capacitance in the tube. And we have built that later on, but even these tiny little details requires development every time, because we don't have the money to buy it, so we need to build it. All our radio equipment, all our antennas are, most of them, homemade and home built. All the radio systems are home built. We are using a small chip that are designed to to be in, you know, the home automation and alarm systems. Those little sensors you have, the wireless ones, little small transceivers in those. If you take them and control them by an Arduino, well, an Atmel CPU, and then you put an amplifier on, then you have a perfect telemetry system for a rocket. And it costs like 50 kroner. So it's fantastic. And then of course we have the marine department. This is where the bulk of the work is really. This platform, we have built that so that we had something to launch from. We have to sail that platform to see, remember the first drawing I showed you, we sail from Copenhagen to Bornholm on that. It takes 24 hours, and you can see this plate here. The plate is here, so because these are just like whole plates. This piece of wood is here so that the crew can be there in their sleeping bags and they won't get wet. So they're sleeping here while sailing to Bornholm. I have never been on that trip, but everyone who has done it says it is the most fantastic experience of their lives. Sailing 5 knots on this platform with a rocket and waving to the Swedish Coast Guard when we are passing by. Yeah. And there's a lot of stuff related to maintenance of ships and all. This timeline was built in 2018. We are working on the Speaker rocket. It's now 2023, and we are not there yet. We had a little pandemic, and we had a lack of money, and we have unforeseen events. But we are working on it, and hopefully we will get there. And I brought this little picture also now. Andreas is on the International Space Station, but back when he was there the last time in 2015, he, as one of his personal items, he brought this with him and sent this picture down from the space station. And we have this hanging in our workshop. That was quite fantastic that day. And that's it. I hope you enjoyed it. And if any of you have any questions, you can approach me afterwards, and I'll be happy to answer them. Thank you.